Boom. All right, so guys, looking at the beginning of chapter 19, and then realizing that chapter 19 we are doing immediately after chapter 5, which would tell us that there are connections between the two. And then, guys, looking at your summary of chapter 19, I have a question for you, and there's a right answer. What is the most important idea in chapter 19? Guys, this is sort of like your typical American story, climax and resolution. Other cultures don't work that way. But guys, in our storytelling form, we're building to a point, a climax. And guys, what are we building to? And I want to give you a minute to think about it. Guys, looking through your notes, looking through chapter 19, where is all of this headed? Don't say a word. Where is all of this headed? And again, guys, it's not rhetorical, and it's also not open for debate or discussion. There's an answer. Where is all of this headed? If you need to flip through the chapter, knock yourself out. Not yet. But no. Ivan is hazarding a guess, but he was wrong. Entropy is a step on the journey. Stop it. Stop. No talking. Reach above you. Oh, there we go. All right. You guys have a minute to think about it? Talk to the person next to you. Where is this all heading? And the answers are not free energy or entropy. Both steps in a direction. All right, guys, we're going to go group by group. All right, here we go. We're going to go ladies first. Ladies first. And whoever gets it right first, there's granola bars on the line. Are you a group of your own? All right, here we go. What's the main point? Main point.
Understanding the temperature.
Incorrect. Main point. Bad. Main point. No. Now we got the guys. Gentlemen. Also incorrect. Boys. No. Go. That's it. Go, boys. No. No. Oh my goodness. I'm going to be up here eating my... No, we're going to be here all day. You guys are pathetic. What? No. All right, but guys, tongue out of it. Actually, my tongue was never in my cheek. There is one and only one outcome that all of this is leading to. So let's think. Back in chapter... No. Stop. We're ready. So, guys, back in chapter 5. What was chapter 5 all about? Enthalpy and heat, right? Then, guys, in chapter 19, we bring in this idea of entropy, which is a sister concept to enthalpy. But, guys, that is all leading to, well, really what the AP authors would tell you is the most important idea. But, guys, it's also a critical universal concept that you've got to understand. And, guys, it's simply this: spontaneity. That is the most important thing in chapters 5 and 19. It comes down to the simple idea, is a process spontaneous? And so, guys, that is where we're headed with this conversation for the next 2 days. Now, guys, with that said, we need to have another conversation. The end of the quarter is next Wednesday. Sometimes this comes together differently than this quarter. Last year, this is the way this worked. 2 years ago was COVID crazy and nothing worked. But guys, the bottom line is your grade this quarter is going to be determined by the test that you're currently rewriting. We are going to take the next test on Friday. But there's no way that we can get it graded, returned, rewritten, and then regraded before next Wednesday. So we're not going to try. So guys, this is how we're going to handle the end of the quarter. Friday is going to be the deadline for any late work. That includes homework, chapter summaries from this class, and test rewrites. If you don't have it done by Wednesday, your drop dead is Friday. Then, guys, we'll talk more in third period, but I'm all caught up with grading your lab work. Don't check Skyward. We'll talk in a couple minutes. But, guys, the deadline for both of our classes is going to be on Friday, and we'll also take the test on Friday, but we're going to push that to second quarter's grade. So some of you are going, oh, crap. You guys understand data. You understand that small pieces of data are not accurate representations of trends or truths, right? So, guys, if you're doing everything you can to help yourself, like turning in chapter summaries, done and on time, doing your homework, that sort of stuff, guys, we will talk about how we're going to handle a one-test quarter. Trust me to not let this hurt you unless you're hurting yourself. So if you're turning stuff in and on time, and if you're doing the stuff you should, we'll talk, but trust me, it'll be okay. Okay, all right. So, guys, with that said, entropy is the deal. Not entropy, sorry. Yeah, my bad. Guys, spontaneity is the most important thing and the big idea from this unit as it relates not only to your understandings for the test, but also just your understandings of how this world works. So, guys, I printed for you your class notes today. Thumb through this and you'll quickly understand why. This is dense, dense, dense material. Like crazy dense. So, guys, what you're going to find is that I dropped off a couple of the slides from your notes. Simply because that way it then fit on 2 double-sided pages. For example, you don't have the cover page. And then, guys, you're going to find out you actually don't have the first slide. The notes pick up on the second slide. But, guys, let's be clear on this. I think you understand this. Guys, well, actually you don't, because none of you do this. Guys, in college, this will save your butt. Professors many times will actually post all their notes for the entire year online, and you can print their entire year's worth of notes. They don't care if you're there. They don't care if classes get missed. Guys, they have a syllabus, and they follow it. And their notes have been their notes for years and years and years, and they can I can't do that because we're reflexively changing things. But guys, your college professors will post their notes way in advance, get them and print them. But then, guys, what do you do with these once you got them? Annotate these things. Guys, write all over this stinking stuff. Go in, wait a second, this, that, the next thing, we're going to talk. But guys, that's the way that you want to handle this, is not be passive, be more active as you annotate into these notes. So you guys ready to go? All right. So guys, this is not stuff that you can or should write down. But guys, the idea is this. Let's make sure we're clear. What is, that's frozen. Guys, what is the most important concept in chapter 19? Spontaneity. Guys, you are going to see, and this is where we're going to get on Wednesday, there's almost every year there's this question. Here's a process. Is it spontaneous at these conditions? And if it's not, what conditions would make it spontaneous? So guys, this is the most important thing in the chapter, is spontaneous processes. Ooh, maybe I should have given you this slide. Let's just know, because we'll define it later. Yeah, you'll be okay without it. But guys, let's just do the, I think so guys, what does it mean if something's spontaneous? It happens. Yeah, I like that. It just happens. It happens without outside intervention. So guys, and you're not writing this down, but guys, the spontaneous process is a process that happens without outside intervention. Give me examples. Things that just happen. Go ahead. Yeah.
Rusting.
Say it again.
Rusting.
Ooh, tell me more.
Because things are just left outside. Any changes.
I thought you said resting. Oh yes, rust is a spontaneous process. Guys, we allow these things to sit outside. Ooh, I'm going to come back to that in a minute. It's even more interesting that you know. But things rusting, all we need is water and oxygen, and things rust all on their own. Guys, other things that are spontaneous. Yeah. Ice melting? What if it's 20 below zero? Okay. So, but Linz, it brings up a really interesting point, is that and we talked a little bit about this, it's contextual perhaps. So and this is the question that they're going to have you answer on the AP test. So let's take ice melting. So ice melting is spontaneous under what conditions? Yeah, right. So anything above zero. But what if it were below zero? What could we do to then make it spontaneous? Heat it up, right? So if you've got ice and if it's below zero, melting is not spontaneous. So under what conditions would it be spontaneous? Higher temperatures. And that's actually where that's the only thing you have to keep track of in this class, is how temperature impacts spontaneity. And we'll get there. Go ahead.
The whole point of temperature impacts spontaneity.
Yeah.
Way beyond that other being spontaneous. Like, isn't changing a temperature that is not outside intervention?
I see what you're saying, and that's a really interesting question. So when we talk about this, when we talk about outside intervention, I got to get my words right. We are talking about closed systems. Okay, remember closed system, chapter 5, energy can get in and out, right? But matter can't. And remember, we're excluding work. And if we're excluding work, we are talking about the free exchange of energy between the system and the surroundings. So in that sense, when we talk about happening without outside intervention, we exclude the exchange of heat, because heat there's always going to be, anytime something happens, there's an exchange of heat. There's an exchange of energy. Could also be work. So the energy's got to be able to come and go, or nothing would happen. But again, that heat or that temperature can define whether something is happening spontaneously. Because remember, if we come back to heat is the transfer of energy from hot to cold, and that happens spontaneously. Hot spontaneously goes to cold. Cold does not spontaneously go to hot. So because heat transfer is spontaneous, it doesn't break this rule. Is that okay? That's a brilliant observation. Guys, other things that you know to be spontaneous. How about this? Let's go back to our good friend, Mr. Metal Block. So, you ready? We've got a block and it's hovering in the air. And guys, when I let go, what's going to happen? Do I have to do anything to this block to make it drop? No, I just need to let go of it and it drops. So guys, the minute I do that, blocks fall. And at the moment that I let go of this, I don't have to do anything else to it. That is also a spontaneous process. You good on those ideas? Okay, so guys, here then's what we know. Anything that doesn't happen. You ready? Let's do it. Elizabeth, that's a brilliant question. Let me give you a non-spontaneous process. Rise. Come on, baby. You got to go. Get up there. Go. Up. Not spontaneous. Right? Could we make it happen? Yeah, but I got to lift it. And now the surroundings are intervening. And so this doesn't happen all on its own. So it's not spontaneous. So this is a deep thought, and we're going to get into it on Wednesday. Anything that you see happen is spontaneous. Because if it weren't spontaneous, it wouldn't happen. And then it gets even worse, because most things that you never see happen, it's actually the opposite thing that's happening spontaneously. So for example, rise, block, rise, never gonna rise, fall, block, fall. So we're gonna talk about spontaneous and non-spontaneous directions. And that's an even more interesting conversation. Yeah.
So you picking up the block wasn't spontaneous, right?
Me picking up the block was, no, not spontaneous, no. Yeah, because I had to do work to pick it up.
So the question is, my question is,
Yeah.
gravity is also applying force down.
Correct.
Wouldn't that be outside intervention?
So again, in the same way that we don't consider heat exchange to muck with this idea of outside intervention, we also don't consider fundamental forces, gravity, electromagnetism, to muck with this definition. Is that okay? So literally there has to be something in the surroundings like me going, ha ha, and now it's moving. So, and again, there's a lot we need to talk about, which is why I printed the notes. But you're going to find out that every process has a spontaneous and a non-spontaneous direction. And that's where we're going to get.
So pretty much anything that's constant.
I'm always scared of the word like definitives, like always, never, anything, because there can be exceptions to those that immediately prove the idea wrong. But I don't disagree with your thought. So, yeah. And guys, you're going to find this. This whole thing with entropy and the second law of thermodynamics is wackadoo. Like, remember how I told you not to Google enthalpy? Well, you're going to do it anyway. Don't look up entropy. It's crazy. All right. So, guys, that's why my board's not working. It's not turned on. So, guys, this then is where we are, and then we're going to get into some terms. Because can you tell how we're sort of stumbling over terms a little bit? We're not speaking the same language. Now it's really, stop it. There we go. So, guys, these are the things that we need to know about spontaneity right now. What makes... And again, guys, these are not things, they're not in your notes. You don't need to write them down. But guys, this is sort of our list. We didn't talk about balls rolling downhill. We talked about blocks falling. Interestingly, you brought up nails rusting right away. Guys, what about lighting a Bunsen burner? Is that spontaneous? You should struggle with this. Is it spontaneous? Right, but you got to light it, right? Which brings us to another idea about this interaction with the surroundings. So guys, when we talk about spontaneity, we mean continual intervention from the surroundings to make it happen. So we understand that, for example, and this is like a mini Bunsen burner. Guys, we understand, wait for it. Oh, there we go. So, guys, different gas, same idea. We've even got a sparker, right? Because if we do this, this isn't going to burn. But if we do this, it does. We have to add a little bit of energy to get it going. By the way, what is that energy? Activation energy. But guys, once it's burning, it goes. We don't have to keep doing this to keep it lit, right? And so once it goes, it goes. So this is spontaneous. But then, guys, if you put your hand over the top of it, you start to get a sense of why. And guys, the answer is this. Spontaneous processes lose energy to their surroundings. Why do balls fall? They're losing energy. Guys, why does stuff burn? They're losing energy. Why do nails rust spontaneously? They're losing energy. And guys, if you didn't understand this, that's how these work. You guys know about these, right? The hot packs. So guys, the idea here, do you know what's inside here? It's actually ground up nails. Like literally this contains, where's my ingredients? Contents. Ground up nails, water, vermiculite, which is the white stuff they put in potting soil to hold water, charcoal and salt. Water, salt, and nails. What does that do? Rust. And guys, literally, that's what's going on inside of here. Hey, good. Tell us how these work.
Oh, that's your job.
Okay, good. What's up?
I'm just going to respect you, and then also
Oh, I don't know.
it's to clean the desk.
Hey! Somewhere in the stockroom. But in the meantime, you could do this.
Okay, perfect.
Yeah.
Thank you.
Yep.
Thanks, guys.
Do you want these?
Oh, I'm good.
Okay. You can go in the lab if you want. I struggle with public nose blowing. Oh, you're bleeding.
Scratched my arm and I...
Uh-oh. Here we go. Cap.
It's literally like...
Oh no. Oh no. No. I learned in our safety training, if it's warm, if it's wet, and if it's not yours, don't touch it.
Thanks.
There we go. All right. Okay. So, guys, again, back to this, because this ties in tight to what we're talking about. So, guys, literally in here we've got salt, water, and nails ground up into a fine powder. So why does this make heating, rusting nails don't? And the answer is they both do. It's just that these are ground up so fine. What does that change that makes the reaction go faster? Surface area. Tons of surface area. And so all of a sudden we've got this reaction going so fast it gets hot. And it gives off heat. So guys, join me because this is where I'm going to throw you a curveball. Don't miss this. So guys, balls rolling downhill, release energy, kinetic energy. Hydrocarbons burning, release heat. Rusting nails, they release heat. You good on the idea? So guys, we have a general principle then that says this. When reactions happen, when reactions are spontaneous, they release energy to their surroundings. You good? Okay, so now guys, it's time to talk about an exception. Catch.
Can we all get one?
No, per group. I'm going to have you share. Oh, sad. Ivan, help me. Help. Oh, she's got it. Here, coming back. There we go. Just a moment. So guys, make these things work. Read the instructions and make it work. Step number 1, shake contents to the bottom. Step number 2, fold the product in half and press until the bag breaks. The inner bag. Step number 3, shake. No, fold it first and then squeeze it this way. There you go. That'll go.
Oh my god, this is cool.
Okay, now guys, shake. Shake, shake, shake. Now set it down and stop shaking. Set it down and stop shaking. Did you get it? Is it working? Yeah, squeeze hard. Don't be afraid. Okay, now shake. Now feel. Now set it down. Okay. Now guys, once you got it going, set it down. We're all going to count to 5. 3, 4. Now guys, touch it. Still cold? Which direction is energy flowing? In, right? Guys, if this feels cold, it means that energy is flowing from our hand into the pack, right? But notice this. Do you have to continue to shake this for it to continue to be cold? No, because we can set it down and we can stop touching it and the reaction continues to happen. And if we put our hand back on it, we feel very clearly that this is cold. But guys, do you all understand that this is an exception to this rule? So let's talk. Did we have to do something initially to get this to go? Sure. And I don't know if you understood what happened, guys. We broke a bladder of water inside of this, and a reaction is happening between water and a salt. That salt is ammonium nitrate. Ammonium is always soluble. Nitrate is always soluble. It dissolves like the bajinkers. But guys, if you feel it, is energy going, our system is what's in the bag. Is energy going in or out? In. Do you understand that this is a violation of this rule? So guys, for the rest of chapter 19, we're going to talk about what's going on. Because guys, this is true. Don't miss this. This is what makes my job hard. In the next 2 days, I've got to help you figure out how this works. And don't let the quick cold pack be a distraction. Guys, this is true. Energy always comes out of spontaneous processes. Nails rusting, stuff burning, balls go. Guys, this is true. Energy always comes out. But now when you're touching this, you're like, wait, first of all, is this spontaneous? Is this spontaneous? Yeah, it's fun. You don't have to shake, keep it going. Guys, this is spontaneous, but is energy going in or out? It's actually not. Guys, energy is coming out of this. You just have too limited an understanding of energy. But guys, energy is actually coming out of this. The problem is right now you have a physical energy transfer meter, which are these nerve cells that tell you hot or cold. And in your world, hot and cold is the way that energy gets, we're not doing work. So hot or cold is the way that energy gets in and out of these things. And by that, energy is going in. But guys, you're going to find out in a minute that energy is actually, well, not in a few minutes, that energy is actually coming out. So when we talk about quick cold packs, guys, we got to understand that this is true. Energy must be lost to the surroundings in order for a reaction, a process, to be spontaneous. And that's happening here. So how do we explain it? Guys, our definition of energy is way too narrow. There's a whole other side of energy that is, it's as real as a burning lighter. You don't have a problem going, energy's coming out, I can see that, that's what keeps the process going. Well, guys, energy's coming out of this too. You just can't see it. You can't feel it, but it's coming out. And we need to talk about what that energy is. You ready to go? Grab your notes. So guys, in order to have this conversation intelligently, we need some terms. I would encourage you to doctor these up, but it also means we can click through them rather rapidly. So guys, talking about these terms, first of all, we have what is called a reversible process. Linz, we're going to come back to your idea about ice. Okay, so guys, here's what we got. A reversible process is a process in which it's possible for the system to go back where it came from without a net change in the system or the surroundings. So guys, obviously you've got all the notes in front of you, but this is worth drawing. So, and I would encourage you to do this with me. You know where we're going. We got to draw a beaker. And in this beaker, let's draw one ice cube. And obviously that ice cube is surrounded by water. So guys, I don't know how you're going to represent this on your paper, but I'm going to represent it by changing colors. So you guys understand we think in Celsius, right? So 20 is warm. It's like room temperature. So guys, this, at 20 degrees Celsius, which direction is the phase change happening? Is ice becoming water or water becoming ice? Yeah, so we've got ice becoming water. Now guys, what about at negative 20 degrees Celsius? Now which direction? Water becoming ice. Now guys, as we close those two temperatures in on each other, where's the tripping point?
0.
Yeah, 0. So guys, and understand that that's not exactly the temperature. It's some tenths of a degree hotter than that. But we're going to say it's 0. Oh, actually, I need that too. All right. So guys, here becomes the magic question. What is happening at 0 degrees Celsius? Well, guys, let's think about what we know. Unfortunately, my ice crystal will not fit in my beaker of water, but that's okay. All right. So guys, what's happening inside a beaker of water? What's it look like in here? Mosh pit. Full-on craziness. Some of them are moving fast enough they jump out the top. We call that evaporation. Guys, it's a madhouse inside of here. Now, guys, what's going on inside of here? They just sit there and vibrate, right? So which one's got more energy at the same temperature? The water, because it has more freedom of movement. So guys, these have more energy than the ice does at the same temperature. So let's say that we're below zero. If we're below zero, these water molecules have lost so much energy that they run into the ice crystal and they stick and the ice gets bigger. Now what if we're above zero? Well guys, then this starts vibrating so fast that it melts and they start going into the liquid phase. Now guys, this. What happens at zero? These are still vibrating. These are still mosh pitting slowly. But guys, these still, even at 0 Celsius, these dudes have degrees of freedom. They can move past each other. So guys, at 0 degrees Celsius, which one has more energy, the liquid or the solid water? The liquid water, more freedom, no intermolecular no structure. But guys, here's what happens. This water molecule with a little bit more energy runs into the crystal. This is at 0. Runs into the crystal. Does it gain or lose energy? Loses energy. Where does the energy go? Into the crystal, and one of these goes away, and for every molecule that freezes, a molecule melts. So what's the net change? 0. But guys, watch. We've got a process going in this direction, and we've got a process going in this direction, and those cancel out. What do we call that interesting set of conditions? Equilibrium. So guys, this is the deal. When we have reversible processes like ice melting and freezing at 0, that by definition is a system at equilibrium. That's what it means to have like changes canceling each other out. So Elizabeth, you mentioned this. We said, what's happening at 0? And you said nothing. And visually, that's true. Guys, if you were watching this, I can't do that. If you were watching this at 0 degrees Celsius, what would you see? Nothing. The ice wouldn't change. The water wouldn't change. So guys, we've got freezing and melting happening at equal rates in both directions, and they cancel each other out. So we would see no change. But guys, there's change going on like crazy. It's going in both directions at once. But the net change, what we would observe, is 0. Is that okay? Does that sit okay? Joni, you've been sitting on a question for a minute.
So it's just with spontaneous reactions.
Okay.
They all lose energy, right?
Yes, but we're not there yet.
So every reaction we talk about, every spontaneous reaction we talk about,
Okay.
it looks like it was losing energy. Do anyone lose energy first?
Yes, absolutely. Oh my gosh, yeah. Like that's what makes our cars go, right? But we are excluding work. So work will, even after the craziness of chapter 19, we are still excluding work so we can talk about enthalpy. There's another way for energy to change. That's where we're headed, yeah. It would, yeah. So, and it's a whole other form of science. A great example is this. Have you ever had a chocolate bar melt in your car? And then when it refreezes, it doesn't look like it did before. The reason is because how the crystal forms. So Hershey's and other chocolatiers are really good at getting molten chocolate to solidify in a way that makes it look glossy and attractive. If the chocolate freezes under other conditions, you get weird crystal structures that make it look like white and chalky. That's actually what's happening. So yeah, absolutely. You guys good on this idea? All right, let's keep going. So now guys, we have irreversible processes. So guys, irreversible processes are processes that cannot simply be undone by reversing the events that caused it. Now guys, this is where we've got to be really careful. Understand that that an irreversible process can be undone. It can go backwards. But when it goes backwards, it goes through a different path, and therefore it has different values for Q and W. We're going to talk about that in just a minute. So here's where we are, guys. We've got our big umbrella concept with this, which is spontaneity. Then we've got this idea of reversible processes. Guys, reversible processes are processes that are at equilibrium. They are undoing themselves at the same time. Then we've got irreversible processes. Irreversible processes can't simply be undone like ice freezing and melting. They don't just cancel each other out. They can go backwards, but they have different work and heat values in order to undo them. Are we sitting okay with that? Let's summarize and then let's talk. So guys, the summary then goes like this. Spontaneous processes, first of all, will proceed without outside intervention. Number two, always have a direction that they go. And three, they are irreversible. Guys, let that sink in, and then we're going to talk about some examples. So guys, spontaneous processes, one, happen without outside intervention. Two, always go in the spontaneous direction. And three, they are irreversible. Good? Yeah. Let's do that. Hold on. Where's my block? Okay, good. That's exactly what I wanted to do, is apply these three ideas to all of our examples. So talk to us.
So when you drop it,
Yep.
it's losing energy.
Correct.
So couldn't you just regain the energy by the
Correct, but watch. So that's the idea. So I'm not going to let this hit the table. But here, okay. So the idea is this. So this is our starting position, okay? And when I let go, the block just falls. All on its own, it falls. No, I don't have to push it. It just falls, right? Okay, so now the block is on the table. But again, as Elizabeth, I think, got us thinking, that bugger's not moving, right? That will not simply, this is an interesting way to think of it. That will simply not just rise in the same way it fell, okay? But can we get it to rise? Sure, but now I have to do work. So I actually do have to do this to get it up, whereas it falls all on its own. So that makes it irreversible. Balls, and again, because of gravity, but we're excluding that as a force. The idea is that this block falls on its own, will never rise on its own, but we can make it rise by doing work.
But will it technically never fall on its own? About something?
It depends on our starting point. So and I agree with you, so we need to say that our frame of reference, our system, is a block that has already been raised. And from that point, now we're looking at a process. It's the process of falling. And then we have the opposite process, rising. And things fall on their own. They don't rise on their own.
So the net change is like we're changing the system does.
Okay, now that's the interesting bit. And let's talk about that. Because remember when we messed around with this block? And didn't we say like 100 joules? Right? We said when we picked it up, it had like 100 joules of potential energy. Here's the thing. Right now, this has 0 joules of energy, right? But if we raise it up here, now it's got 100. Then when it falls back down, it goes to 0. Now, so again, our process is falling, right? So when this, I got to stand up. When this falls, how much energy does it lose? 100 joules. Now, we can get it on its own, it won't go back up, right? But if we want to take it back up, we have got to add exactly as much energy as came out of it when it fell. The difference is heat and work. When this thing falls, it falls spontaneously. When we pick it back up, now we're doing work that wasn't necessary for it to fall. And so that's what we mean by they have different pathways. Falling is a spontaneous all on its own pathway. Going up is a pathway that requires work that falling doesn't require. Yeah, go ahead, Ivan, just a second. Good for you. And so we've got this idea of potential and kinetic energy, right? But at this point, we don't have to talk about the total internal energy, the kinetic and potential. We can just talk about energy. And right now, energy is 0, but we're starting here. And now this has energy, and the energy comes out. In order to make this go up, we've got to add that energy back, but we add it back through work, which is not how it fell. That's a great question. Just a second. Go ahead.
So like if water moving up a tree,
Oh my gosh, like crazy. But the thing that's really cool is, and forget, you probably know more biology than I do, isn't it actually that the sun is doing work? that in the canopy of the tree, the heat of the sun is causing water to evaporate, which causes like a vacuum, which causes it to draw water up. So work is being done, but I think it's being done because like trees don't have pumps, right? Do they? I don't know. I don't think so. So yeah, so I think the work's being done by the sun, but absolutely, there's work being done. Yeah, just a second. Go ahead, Claire.
So everything makes sense what you're saying, but with the definition of universal.
Yes, yes.
Saying no, you can't change.
Yes.
You have your head rules, and your mind is under rules to do that.
But you have to be careful because I'm changed, right? I mean, it depends on how far we think about this backwards. But for me to let this, and again, our starting point's here, right? And I've always longed for a better example so we don't have to have this contrived starting point. And there's tons of like biological and physical and chemical, but this is so visual. So let's start here. And when this falls, I'm like, no harm, no foul, right? I didn't change. I didn't do any work or get hot or I just let go, right? But now when I lift this, I'm changing. I'm losing energy. I'm sweating because it's heavy. I don't know. But it is changing me in a way that falling didn't. So the energy change is equal. But again, the pathway through work and heat are not the same values. And that's what we mean by change. Is that okay? Jonah?
Well, I was going to say that a tree creates water by like creating negative pressure.
Yes, a vacuum. Yeah, right. And isn't that from the evaporation at the top?
I'm not sure exactly how it does it, but
Yeah.
it's like not just a vacuum. It's
Yeah.
less pressure than a vacuum.
Oh, sure. It's certainly not a vacuum or the tree would implode. But yeah. Same idea. You guys okay? So guys, let's do this. Let's unpack our other examples. Ready? So you guys don't even know this. Inside of this is butane. It's C4H10, 4 carbons in a row, surrounded by hydrogens, oxygen in the air. When we do this, what are our products? Carbon dioxide and water. Now guys, could we take the carbon dioxide in water and rip it apart and reorganize it and turn it back into CH4, C4H10, and oxygen? Yeah, you understand that that's what trees do, right? If you don't understand this, we need to talk. So, guys, you understand that the chemical process inside of trees is exactly the opposite of the chemical process inside of us. So guys, what happened, this is way oversimplified, but what happens in trees? Carbon dioxide and water make sugars. Yes? Sugars. Carbon dioxide and water make sugar. This is not a sugar, it's a hydrocarbon, but the analogy stands. So guys, inside of trees, carbon dioxide and water turn into sugars. Then we eat those sugars, and what do we do with them? Turn them back into carbon dioxide and water. You guys understand that, right? In our world, we have plants that make sugars, and then we have animals that eat the sugars, or the things that eat the plants. You get the, but guys, so guys, understand that taking carbon dioxide in water and turning it into sugar is reversible. It just doesn't happen on its own. We got a lot of work and heat going on. Is that okay? And then guys, what was the last one that we used as an example? I don't even remember. The rusting nail. So guys, can we take the rust from the nail and turn it back into iron and oxygen and water? Sure. Just takes a lot of work. Get the idea? Okay. So guys, with these ideas, let's see how you do. What's our girl's name? Is it?
Yeah.
Babs. This is not Babs. I know, Babs is coming. I know, Babs is on the way. But this ain't no Babs. Oh no. Come on, baby. Hey, there we go. All right, guys, you ready? Oh boy. This is big. But guys, seriously, this is crazy. If you understand what's going on. So, guys, what we've got here is obviously eggs up in the air. kind of like our metal block up in the air. So this is our starting point. And when we click, what are the eggs going to do? They're obviously going to fly up into the air, right? Yeah, right. Or they're going to do this. And guys, that is spontaneous. Eggs falling and smashing is spontaneous. How do we know it's spontaneous? Happens all on its own. But now, guys, this. Is it reversible? Could we take the yolk and the white and the shells and all of that stuff and knit it back together and turn it back into an egg? Yeah, in theory we could. That's what happens inside of chickens. So guys, in theory, we could put this together and turn it back into an egg, but don't miss this. It's going to take a lot of work. Seriously, guys, that's important. It's going to take a lot of work. A lot of work. But guys, watch. I don't know why you're giggling, but it scares me because you're missing the big idea. What am I missing? So, inside of chickens, never mind. No, but guys, seriously, this is the groundwork for everything we're about to do. Don't miss this. So, I think I can reset this. So, let's do it again. Okay, so guys, egg falls, smush, splat, right? And guys, we lost a bunch of energy. Energy went into destroying the egg. Energy went out as sound. Energy went from the thing. Because lots of energy. So, that's spontaneous because is it reversible? Will those eggs ever magically knit themselves back together and jump up into the air? No. So that makes it spontaneous because it's irreversible. Stop right there. Do you see the connection? Irreversible means doesn't go the other way all by itself, and if it's irreversible, it's spontaneous. Yes? Is that okay? Now, guys, check this out. We've agreed that we could make this happen, right? It could just magically come back, not magically, but we could put this back together as eggs. Again, I'm not going to say it again, but that is what happens inside of chickens. But, so, guys, it could go back, but do you now understand that this is the non-spontaneous direction? So reactions or processes that are spontaneous have a spontaneous direction, they always go. They have a non-spontaneous direction, they never go. And therefore, anything that's spontaneous is irreversible. Is that okay? Now, guys, this. We're going to talk about work only momentarily. How much work does it take to drop eggs? Not much. But guys, how much work does it take to put them back together? A lot. But guys, here's the thing you got to understand. Work is a way of exchanging energy, right? Don't miss this. When these eggs fall, it appears as if there isn't a lot of change. Well, I'm sorry, that there is. Well, so how do I say this? So when the eggs fall, let me do it this way and then we can talk. So guys, the amount of energy that is lost when these eggs fall and break is equal to the amount of energy needed to put them back together again. Just a second. Let's say that again. The amount of energy that's lost when these eggs fall is equal to the amount of energy that it would take to put them back together and then pick them up. But guys, if you look at that, that should seem impossible, right? How much work does it take to put those eggs back together? A lot. So guys, if it takes a lot of work to put them back together, there must be an amazing amount of energy that goes into them falling apart. And there is. But it's not work and it's not heat. Do you see where we're headed with this? Guys, there's another driving force in this universe that causes things to happen. And it's all the unaccounted for energy change that we see in this. Guys, when these eggs fall, you're like, hey, yo, they're just going to fall and they're going to bust apart. That was easy. So certainly putting them back together has got to be easy as well if the energy change is equal. But guys, it takes a lot of work to put these back together, which means a lot of energy must have been lost when they fell. But guys, the energy was not lost in the form of heat, and it was not lost in the form of work. How was it lost? You've read chapter 19. How was it lost? Nope. How was it lost? You ready? If you don't know immediately, this makes you really thankful for me. Because, guys, this was all trapped in chapter 19, and you've read it. So, guys, look away from your books and join me. I won't ask it. I'll ask it rhetorically because you don't know. But let me get you there. So, guys, when we drop these eggs fall and they break apart. And you're like, oh, that was easy. But it should then be just as easy to put them back together and turn them back into eggs, but it's not. So guys, where is all the energy lost that is then have to be accounted for when we put them back together? And guys, it's an energy that we've never even talked about before. It's the energy of disorder. Stop. It's the energy of disorder. Guys, these eggs that are up here in the hand are super organized. They've got a shell, they've got a whites, they've got a yolk. They're all organized and they're all in position. But guys, when we drop them and they shatter, what about the organization of this? It's a stinking mess. Guys, this is highly disordered. So the energy that is lost in this process is largely lost in the form of disorder. And if we want to put this back together, we've got to overcome that increase in disorder. So now, guys, this. Grab your quick cold packs. Still cold? Still cold. A little bit. But guys, here's the idea. Coming back to our original thought. Guys, join me and watch. So is energy going, is heat going in or out? In. Heat is going in. But guys, energy is going out. In what form? And guys, the answer is disorder. Inside this quick cold pack, the process that is taking place is causing the disorder. Ooh, I got you. Guys, the process that's taking place inside this quick cold pack is causing the disorder to go up so much that it offsets the intake of energy in the form of heat. So guys, the net energy change inside this pack is a net loss of energy, but it's not being lost as heat. It feels cold. It's being lost as disorder. And guys, please hear this. In this class, we will never talk about order. We will talk about disorder. So guys, the energy change in this pack is a net energy loser. Heat's going in, the energy that's coming out is the energy of disorder. Yeah. Randomness, yes. And so, not in this class, but if you choose to do chemistry big time, and if you take PChem, this is scary, like terrifying. Here, I'll turn it so you can't see it. It's horrible. But in PChem, and we'll talk a little bit about this maybe tomorrow or Wednesday, randomness and disorder are the same thing. And we'll, if you're interested, we can talk about it quickly. It's about microstates. And it becomes a statistical problem with tons of calculus. But basically the idea is the more potential places something can be, the higher its randomness and therefore its disorder. A great example is this. Water, ice is highly organized, relatively low disorder. But when ice melts, it turns into liquid water. Higher disorder because these molecules can be in different places. So understand, though, that these can both be at 0 degrees Celsius, right? And so if we want to take the ice and turn it into water, we have to add energy to make it melt. Remember when you learned that last year? But we also learned that the temperature doesn't change, right? The molecules don't move any faster. So where is the energy going that we dump into the ice to turn it into water? And last year we said it's the phase change. We call it melting, right? What's really happening is that energy is going in to increase the randomness or the disorder, which we didn't talk about last year. Do you guys are we okay? Can we give that thing a name? Guys, it's called entropy. That's what entropy is. Entropy is disorder. It's randomness. But guys, entropy is disorder, and that's the driving force that makes this happen. Guys, in the same way that releasing heat makes things happen, increasing disorder makes things happen. Go ahead, Jared. Do you mean charge? I think you mean heats of formation. That's exactly why. Yeah, that's it. Wow. Can we say that again? Guys, remember back in chapter 5 when we were talking about heats of formation and some of them were positive? That's exactly why. There's an offsetting change in disorder or entropy that offsets that net energy gain. Now, Michael, I heard you say a couple minutes ago, free energy, right? You're like, hey, so free energy, you're going to find out in a day, is the bringing together of the change in enthalpy and the change of entropy, disorder, and that becomes the final say in terms of whether something's spontaneous or not. We'll talk more later. So guys, how are we sitting with these ideas? Let's review. First of all, if we've got an egg in the air like so, if we let go, it falls. So guys, that makes falling spontaneous. Is it reversible? No. Please, guys, don't screw this up. This is not reversible. Can it be reversed? Sure, but reversible means goes the other way all on its own, like ice freezing and melting at 0. Guys, don't confuse reversible with undoable. We can undo this, but guys, reversible means it's going in the same direction and it cancels each other out. Because there's only one example of reversible, and what is it? Equilibrium. Guys, reversible means equilibrium. You've got it in your notes. If you want to circle that like 11 times, guys, reversible means equilibrium. It's on for you, the first page at the very top. Reversible processes, these are at equilibrium. Do you see it? It's there, right? Yeah, it's there. Yeah.
So with the egg dropping,
I got you, Linz. Yeah.
So with the egg dropping and breaking,
Yeah.
that
Yes.
so then, sorry, when you're talking about like endothermic and exothermic reactions, you're talking about how the like desynthesis to one of the reactions.
Hold on, let me slow down with you there. So when we talked about endo and exothermic, what?
We said that whenever bonds break,
Yes,
the system changes, right?
always.
Yeah. And so you use the example of like breaking a rock and you have to put energy into it
Uh-huh.
to break it open.
Uh-huh.
So then why does the egg breaking lose energy if it's breaking? Should it be gaining energy because you have to put energy to break it?
So yeah, Jonah, that's a really interesting observation. And I love how you're sort of error checking your thinking. Did you guys understand what Jonah said? Because it's a really interesting and brilliant observation. So we said that breaking bonds is endothermic. Energy goes in, right? And so why is it that breaking the egg is then an energy loser? And the answer is because you're talking about you're considering those two processes to be equivalent, and they're not. So a lot of the energy that's lost in the breaking of the egg is in the falling and not in the breaking. But in addition to that, the additional energy, and this could be our connection, the additional energy that is well, how do I say this? So, no, let me back up. So a lot of the energy that's lost is lost in the falling. But then when the egg hits the ground, hits the whatever, there is an intake of energy, right? Because we're literally breaking, it's probably intermolecular forces and not bonds that hold the shell together, but there's something that holds that shell together, and energy has to go in to break that shell. But the minute that shell breaks, there's also then another net release of energy, which would be the increase in disorder. So when we go egg fall, loss of energy, egg break, a little bit of an intake of energy to break those bonds, but then disorder because we're getting a much more disordered system, the overall picture is a loss of energy. And we know that because it's going on its own. But when we then talk about breaking like a rock with a hammer, we're looking at a much more isolated event, right? We've got rock and we hit it with the hammer and energy goes in, but you ready for this? Energy also comes out. In what form? Well, disorder and sound, right? And so we've got energy coming out of sound, we've got energy coming out. But so this is a great example of system and surroundings. So imagine that this is a rock. And if we hit it with a hammer, the breaking of these bonds is endothermic. But there are other things that go on that could make the whole process exothermic. Or at least energy losing, maybe not in the form of heat.
So the egg breaking itself
Yeah.
gains energy, but the other things make it a little bit of energy. But
Yeah.
there's more energy.
Yeah, the overall change is a net energy loser. Is that okay? But again, it really does come down then to what's our system. Like if our system is just the eggshell, this would be taking in energy. Well, no, because of the amount of, this is where we're in no man's land because we haven't quantified entropy yet and we need to. But if we just think about it conceptually, energy did go in to disrupt the bonds that held the shell together. Then looking at the net energy change, we'd have to bring the rest of it in. Is that okay? Linz, what did you want to do?
So you were saying that every spontaneous process is irreversible.
Hold on. Every spontaneous, yes, that's true.
Every irreversible process.
That's not nice. Is every irreversible? Yeah. And the reason is because they're can I say self-referential? They're the same. So if something is irreversible, let me say it this way, because I'm not trying to nitpick, but any process that is spontaneous has a spontaneous direction that always goes. It has a non-spontaneous direction it never goes, and therefore it is irreversible. Is that okay? But then understand that when we talk about that non-spontaneous direction, we can make it go that way. We just have to do different work in heat. Is that okay? Yeah. And guys, this is why I printed the notes for you, right? We're chewing on some really like intricate and fine details. The only thing worse than learning this is trying to teach it. But you guys are doing awesome. So do we feel comfortable with reversible, equilibrium, irreversible, spontaneous, and it has a direction that it always goes, the spontaneous direction, and a direction it never goes, the non-spontaneous direction. But we can make it go the non-spontaneous direction. We just have to do different types of work and heat. Yo? Yeah.
So I like chuck it in the wall.
If what?
If you like chuck it in the wall,
Yes.
that's not spontaneous. But
Yes. Okay, so if you chuck the egg at the wall, well, it depends on when you're talking about, because the minute you let go of it, it's on its journey and there's not much you can do to save it. So the minute you let go of it, it becomes spontaneous. Then you're an evil, evil person. Yeah, so what are you trying to get at?
So you said
I like the way you guys keep saying "you said," as if this is my fault. It has been said. Okay.
That any irreversible process is spontaneous, but neither direction would be spontaneous.
I'm not making that connection. Help me.
So, okay, I'm not sure this is right.
No. Keep. Let's think about it.
So you said that any irreversible process is spontaneous.
Hold on. Let's stop there. Any irreversible process has a spontaneous direction.
Well, that's not spontaneous. And it's irreversible.
Why isn't it spontaneous?
You're just putting work into
Oh, I see what you're saying. So, guys, help me with this because it happened, right? And if it happened, it's spontaneous.
You said lifting the block is spontaneous too. Does that happen?
But yes, but we weren't looking at lifting the block. We're talking, so maybe let's use that as an example. So, can you help me?
This just
Save me from Michael is what it comes down to.
is the fact that the egg broke against the wall and didn't just keep going straight.
Could be. Could be. Maybe. Let's go back to the block.
Correct.
It's the same thing. So right there, you dropped it.
Yeah.
Like a float away.
Yeah.
You chuck it. It's more energy going into it, but it's gonna be even more energy to put it back.
Yeah, I because you're going to get more splatter, right? But I like where your head went there.
Put
'Cause-
more energy.
Yeah.
Let it go. You actually.
We need exactly. But Joan, I think in this example, it comes back to your idea about what does it mean to have external intervention? Because if we're starting here, it drops. If we're starting here, when it leaves my hand, I'm no longer interacting with it, and at that point, it becomes spontaneous. But back to your idea, because I understand what you're saying, that block won't lift its own. But if we do this, it just went up. So something spontaneous happened. But I think at that point, we have to talk about the internal processes inside of me that made that happen. I think. Yeah, right? I know. Again, Michael's just trying to blame this on me. So I hate to do this, but I wonder if chasing down these minute details might become unnecessarily distracting. Maybe. I am, however, comfortable with the idea of letting go of the block or the egg. And when you let go of the egg, at that point, the surroundings, is no longer interacting with the system. And from there, it becomes spontaneous. Because really, throwing is just horizontal dropping, just a different force.
Well, then I said you were gonna like
I know. And again, I think the reason, forgive me, this sounds insulting, but it's not. I think the reason your question is intriguing is because we're having a hard time defining system. Because the minute we define system properly, because the problem, so maybe, I've never thought of, this is me thinking in front of you, right? But I think the difference may be that imagine this is our egg, right? And imagine that we throw it against the wall. We're now part of the system because the egg is still in contact with us. So I wonder if the reason that thought is confusing is because our system became undefinable because we're a part of it. Maybe. I'm not sure. I don't know that it's going to keep me up at night, but I'm interested in the idea. It's really, I don't have a good answer for you. We can say with certainty that if something is spontaneous, it's irreversible, but it can be undone. But this bigger question about system surrounding interactions and the egg against the wall, I really think it comes down to us having trouble defining the system, but I'm not exactly sure why. It's a great idea, though. Yeah.
So earlier you were saying, sorry.
Why do I feel bullied? Go ahead. I know. Science is never personal.
Once you let go,
Yes.
it becomes like
Irreversible. Yes.
But up And
Yeah.
that would be not spontaneous, so it would be reversal. So, like, what would be the opposite of the forward motion?
Pulling it back, I guess.
Both have energy?
Yeah, but again, the problem is system because, oh shoot. So at that point, we're part of the system.
Yeah.
And there's change happening inside of us at the metabolic and cellular level. So I really, in the same way that Michael's question is intriguing but hard to think about, and we just blew Elizabeth's mind to the point where I think she passed out. So I really think that the problem is that we're just having a hard time defining system in these more complicated examples. Is that okay?
The thing that's hard for me to
Yeah.
grasp is that there's a reverse for everything. It feels like
Yeah, everything can be undone.
But does one of those directions have to require the spontaneity and the lack of outside systems? Or is it just...
Yes. Yeah. Again, yes. So, and that's what I'm trying to get at is what are the underlying principles that we need to understand and not muddle because of our inability to think about complicated systems. And so what you're saying is exactly right. In order for something to be spontaneous, it needs to happen without outside intervention. But realize that doesn't mean no intervention with the outside. So it can lose energy, right? So when this thing falls, it's losing energy. It's just not taking in energy. Is that okay? So fundamentally, things that are spontaneous are irreversible, which doesn't mean they can't be undone. It just means not through the same pathway. And they lose energy to their surroundings and or they make disorder go up. Is that okay? Are we that? So guys, we obviously, and I knew that we're not going to get done today with this. I was fairly sure. Test is not Friday. But I do want to wrap up with this to give us a jumping off point for where we're headed next. And guys, it goes like this. Turn to this slide.
Does it say what atomic pressure is? It says I am gas.
I am gas.
All right. So guys, here's what we've got. So guys, we have, imagine two propane tanks connected with a hose that has a valve in the middle. And one of these propane tanks is full of gas, and the other one is a vacuum. It's empty of gas. Now guys, if we were to open the valve so that these two tanks can interact, what is the gas going to do? Not fill both. It will both be, and if we're giving it numbers, if we have 1 atmospheric pressure of gas on the right, when this is done, what will the pressure in both tanks be? Half. Now guys, do we have to squeeze this tank to get the gas to go over there? Do we have to heat it up in order to get the gas to go? So we don't have to do work and we don't have to add heat, right? And guys, as a matter of fact, the temperature doesn't change. So now we've got a problem. So when I pull out that barrier, we're all comfortable with the idea that these gases are going to spread out evenly. Is that spontaneous? Yes. Let's put it to the test. Is it reversible? No. Because guys, how long are we going to have to wait for all the gas to all go back over here? Ain't going to happen. So guys, it has a spontaneous direction, it has a non-spontaneous direction, and therefore it's irreversible. Yes? Okay. So guys, and we don't have to heat it, we don't have to squeeze it, it happens all on its own. So what is the driving force, if you will, that causes this spontaneous process to happen? Entropy. Guys, entropy is a very real, very mysterious, very hard to define or see, but a very real force in our universe that causes things to happen. And it's disorder. Guys, disorder, not order, disorder. But guys, you can see from this simple system, guys, that disorder is a very real driving force behind this process taking place. Is that okay? So, Linz, was it you that brought up the idea of randomness? Is that okay? So, guys, I don't know that we're going to talk about this, but let's just do this for a moment. So, guys, how does this work? Well, guys, imagine that we have 4. This may run a minute into the bell, but you don't need to know this for the test, but it might be interesting. Let me do this differently. So, guys, imagine that we have 1, 2, 3, 4 molecules in this left tank. Right tank. So now, guys, let's talk about all the possible combinations that we could have, and I'm going to need a pen. So, guys, we could have 4 dots on the right, or we could have 4 dots on the left. What are other possibilities? 2 and 2. 2 and 2. We could be 3 and 1. We could be 3 and 1. But guys, here's the problem. This gets even more complicated because it doesn't have to be the 3. We could have 3 and 1 where this is molecule A. We could have 3 and 1. Thank you. We could have 3 and 1 where that's molecule B, 3 and 1 where that's C, 3 and 1 that's D. We could have 2 where this is A and B, and 2 where that's C and D, or this could be A and you get the idea? Guys, there's a billion different ways that we could organize these 4 molecules. But guys, and that's just 4, right? So guys, how many of these combinations have all the gas molecules over here? 1. How many combinations have the gas molecules over here? There's only 1. But then, guys, there's an uncountable number of different combinations that has the gases spread out. Guys, that is actually the driving force that explains entropy. It's all about probabilities and degrees of freedom. Guys, the minute we pull that barrier out, we have so many degrees of freedom. With that barrier in place, we've got 1 degree of freedom. All of the molecules in the right-hand tank. When we pull that barrier out, guys, we have so many degrees of freedom, they're called microstates. We have so many different possible microstates, and most of them look like half over here and half over there. But guys, those are averages. Guys, understand at any given time, there could be a little bit more over here than there is over here. But as these things move chaotically, they quickly sort themselves out. So the predominant average is half and half. But guys, this is statistics, right? In theory, there could be a moment where this is true. That all of the molecules have moved to the left and there's none in the right. Statistically. But guys, this is only 4 molecules. Imagine if that's a mole of molecules. What are the chances of them all moving to the left at the same time? Get the idea? So guys, when you are talking about uncountably large samples, and when you are then talking about all the different degrees of freedom that those have, like moles, then all of a sudden entropy makes sense because we're talking about averages over huge sample sizes. So guys, let's do this. We are done for a moment. Hold on. If you'd like to learn more about this idea of averages and microstates and degrees of freedom, guys, hold on. Well, you will. That's what we're doing in lab next week. Hey guys, do this. Take a break and we'll talk when you get back. Get out of here.
With cold packs or hot packs?
Not